Hi guys, so in this video I'm going to quickly talk about the lab for this week, give you some hints to be successful in that lab, and what I'd like to remind you of is that I had previously posted a video that went into the lab at great detail. So the very first thing that you want to do when you're starting on this lab is you want to combine your solutions in the virtual lab in these combinations and just see if anything happens at all. And how we're going to observe if something happens is that there will be a new substance formed. So don't be put off if for several of them nothing appears to happen. That's okay. If nothing happens, if you don't end up with any new substance, then you're just going to write no reaction beside the row. So if you mix A and B and nothing else forms, then you'll just write no reaction. Okay, so that's the first thing to do, is check for a reaction. And then you want to move on and you want to determine the coefficients, right? And how you're going to do that is by figuring out how do the moles, not the molarity, but the moles of each reactant and product change. And if you can figure that out, then it's pretty easy to get the coefficients. So that's all I'm really going to say about that. I go into greater detail in that specific video regarding the lab. So check that out if you need some more help there. Okay, so now we're going to look at some of the ALEKS objectives for this week. So this first problem here is all about determining the empirical formula of an ionic compound from the name. So you're going to get the name of your cation first, followed by the name of your anion. And I know that there are two types of ions, right? There are monatomic and there are polyatomic. So normally we're only going to see polyatomic anions. Occasionally we'll see a polyatomic cation. But monatomic anions all have the stem name of the element they are formed from and the ending IDE. So bromide and oxide look like they're monatomic anions, don't they? And then the polyatomic ions, we have to look those guys up in a table. Now, a word of warning, sometimes people will Google the name and it'll come back, or they'll Google the formula and it'll come back with the wrong thing because we're using systematic names. So you've got to be really, really careful. There are also many common names for these things. So looking at this, what I see here is that the cation in the first case is copper 1. So the 1 indicates that the copper has a +1 charge. And then the anion is bromide, which indicates that it is the monatomic anion made from bromine. And as bromine is in group 7A over here, it's going to form a -1 anion. So what this means is that these guys have equal and opposite charge, and when that is the case, the ions will combine in a 1-to-1 ratio. So equal and opposite charge, no need to do crossover. We know that they combine 1-to-1. Now let's have a look at the next one. So the cation is labeled as strontium, but it doesn't have a number after it. So how do we know the charge? Well, we have to find strontium in the periodic table. And strontium is in group 2A, sits next to barium and calcium. There it is. And everything that's in group 2A forms a +2. So my cation is going to be strontium 2+. Now then my anion, you see it's got the stem name for oxygen followed by "ide", and that tells me that it's the anion formed by oxygen. And oxygen is in group 6A, so that means that it forms a -2. So again, we see that the charges on the ions are equal and opposite, which tells me that they combine in a 1-to-1 ratio. So there we are, strontium oxide. So it's not too bad, you know. We just have to figure out what our cation is, and then we have to figure out what our anion is. Okay, so this is about naming covalent compounds or molecular compounds. And how we name a covalent compound is we give the name of the first element unaltered. So we give the name of the first element. You don't do anything to change it. Plus, for the second element, you give the stem name and then you follow it up with the letters IDE. And then once you've got that bit done, you're going to then add a prefix to indicate the number of each type of atom. So I want a table of prefixes, or I want to have committed the prefixes to memory. Now there's a little bit of a rule about the prefixes, which the first rule is if there is one of the first atom, it doesn't need a mono. And then the second rule is if the formula begins with hydrogen, we're going to eliminate all prefixes. We won't put any prefixes in. So let's have a look at this problem. It says, for compounds containing hydrogen, you can give the common name. So there's only one that contains hydrogen, and the common name for NH3 is ammonia. So we got that bit done. And then now we're going to go through and name all of the others. So we give the name of the first element unaltered. So it's going to be nitrogen. And then for the second one, phosphorus. For the third one, also phosphorus. And then for the third one, for the fourth one, nitrogen. Okay, and then we give the stem name of the second element and change the ending to IDE. So what have we got? We've got fluoride, we've got sulfide, we've got sulfide, and then finally we've got fluoride again. And now we add prefixes, but we're going to keep in mind we don't need a mono if there's one of the first atom. And so there's one of the first atom for the first one there, NF3, so no mono required. For the second one there, it's going to be tetra. For the third one there, it is also tetra. And for the fourth one there, it is di. And then now we're going to add prefixes for our second atoms. So for the first one, it's tri. For the second one, it's also tri. For the third one, sorry, we got out, didn't we? Out by one. Tri. Hepta for 7. And then for the last one, it's tetra for 4. Okay. So, nitrogen trifluoride means NF3. Tetraphosphorus, P4, trisulfide, right? Tetraphosphorus, heptasulfide, dinitrogen, tetrafluoride. Here we go. We've checked everything in every possible way. Yep, no problem. You always want to be super careful because every problem in your quiz is worth like more than 10% of your grade. So I just looked up this little table in the book and copied and pasted it into my notes. All right. Naming binary ionic compounds, we have to give the formula and then we have to give the name. So what I suggest doing is giving the name first. So how do we give the name? We write the cation name and then we give the anion name. Now the anions, as I said, can be of two types. They can be polyatomic or they can be monatomic. And when I look here, they're all monatomic. So to name a monatomic anion, you give the stem name and you follow it with the ending IDE. Now, cations can be of two types as well. They can be fixed charge, where we don't need to include Roman numerals, and they're going to be for your group 1A, 2A, 3A, silver, cadmium, zinc, aluminum, or silver, cadmium, and zinc. And so, or they can be variable charge, where we have to indicate the charge with Roman numerals. Now, in this case, the cation present every time is calcium. And calcium is in group 2A, sits underneath magnesium. And so calcium is a fixed charged cation, so it doesn't need the Roman numerals. Because it's fixed charged, it doesn't need the Roman numerals. And when you name a cation, you just give the element name, and then if needed, you give the charge with Roman numerals. So this is going to be really easy. So all four of these guys are just going to have, for the cation, calcium, 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 with no Roman numerals. And now I have to name the anions, and the key thing here is that these are all monatomic anions. You see that only one atom there, so we just give the stem name followed by the ending "ide." So it's going to be phosphide, nitride, oxide, sulfide. Phosphide, nitride, oxide, sulfide. And if you're uncertain of the stem names, you can find tables of stem names of the non-metal elements on the internet, and then you can be really super sure that you've got everything. Now, my preference is, whenever you're asked to write both the formula and the name, is always begin with the name. And it's just the name of the cation followed by the name of the anion. For ionic compounds, never use prefixes. Never use prefixes for ionic compounds. Alright, so now let's go on and do the formulas. We have two rules for the formulas, right? When the charges are equal and opposite, they're just going to combine 1 to 1. So let's see if we can find any where that is the case. And clearly it's the last two here, isn't it, right? They have equal and opposite charges. So calcium is going to combine 1 to 1 with oxygen and sulfur. So the formulas are just going to be CaO and CaS, because those guys have equal and opposite charges. Now, when we don't have equal and opposite charges, we're going to do crossover, and then we're going to double check that we can't divide through by a common multiple. So Ca2 plus P3 minus, I need 3 calciums and 2 phosphoruses. So Ca3P2. Now, can I simplify that anymore? I can't. There's no common multiple there. For the next one, calcium nitride, it's the same deal. 2 nitrides, 1 calcium ion. So 3 calcium ions. Ca3N2. Same thing, right? And that's it. So I like to do the name first, and then that way I'm not tempted to write something like tricalcium, right? Because we never use Greek prefixes when we name ionic compounds. Sometimes when you see that, multiplier there in the formula, it leads you to thinking that you need to input a Greek prefix in the name, and you don't. All right, so here we go again. Predicting and naming ionic compounds formed by two elements. So we have to decide whether the two elements given form an ionic compound or not. And so ionic compounds form when we have a metal and a non-metal combining. So that's what I'm looking for here. So let's see what we've got here. We've got cesium, which is a metal, combining with oxygen, which is a non-metal. So yes, that forms an ionic compound. In the next one, we've got cesium combining with bromine, which is also a non-metal. So yes, that forms a ionic compound. So we've got metal, non-metal. Now we've got oxygen, which we'd already labeled, that's a non-metal, combining with strontium, which is in group 2A, which is a metal. So that also forms an ionic compound. And then finally, we've got strontium, which is a metal, combining with bromine, which is a non-metal. So that is also going to form an ionic compound. So in this case, all four of them do. What I like to do now is to name the ionic compound before deciding on its formula. So unfortunately, I've got to do this 4 times because all of them formed an ionic compound. So what I want to remember is for cations, it's important to realize what are fixed charged cations. And it's these guys, right? All of the metals that are in those groups, I know the charge of. For non-metals, the charges go -1 for group 7A, -2 for group 6A, -3 for group 5A, and then for group 4A, they're +4 for the metals and -4 for the non-metal, which is only carbon, but we're just not going to worry about group 4A because it almost never comes up and it's awkward to label. So they're all of my fixed charged ions. And my fixed charge ions don't need me to indicate in any way what the charge is. For my fixed charged cations, I have to indicate the charge by putting it at the end of the cation name in parentheses with Roman numerals. So let's see what we've got here. So element 1 here is cesium. That's my metal. We always do the metal first. It's fixed charge. So I'm just going to write the name cesium. And then oxygen, remember when it comes time to writing the names for anions, we just take the stem name and change it to IDE. So it becomes oxide, cesium oxide. The next one, again, cesium is fixed charge, so no Roman numerals. And then bromine is going to become bromide. Okay, and now we've got our metal is strontium. Be careful, they flip the order. Strontium, there it is. It's fixed charge, so no Roman numerals, so it's just strontium. And then our anion is going to be formed by oxygen, so again it just becomes oxide. And then now finally we've got strontium again for our metal. No Roman numerals because it's in group 2A, and then bromine becomes a bromide. So we got that figured out. Now we need to do our formulas, right? So I like I said, I always do the names first and then I do the formulas. So we've got 2 rules, right? Where either if they have equal and opposite charges, they combine 1 to 1. So cesium's in group 1A, so it's +1. And oxygen's in group 6A, so it is -2. Okay, bromine's in 7A, so it's -1. So oxygen -2. So these guys have different size charges, so we're going to do crossover. And so we need 2 cesiums and 1 oxygen, and we can't simplify that any. So, so we're just going to leave that be. So it's CS2O. All right, next one, we've got cesium still +1. Now we're with bromine. Bromine's in 7A, so it's -1. So those guys have equal and opposite charges, so they combine 1 to 1. Cesium bromide. Now we're going to be dealing with a bunch of compounds containing strontium, or 2 of them, not a bunch, but 2 of them. So strontium is in group 2A, so it forms a strontium 2+. We've got 2 of these guys. We may as well do both of them at the same time. The first one is going to combine with oxygen. Oxygen's in group 6A, so it's -2. Or they're going to combine 1 to 1 because they have equal and opposite charges, so that'll be strontium oxide. SRO, and then bromine is in group 7A, so it's -1. So they don't have the same size charges, so we've got to do crossover. I'm going to get 1 strontium and 2 bromines. So it is CS2O, CSBr, SRO, and SRBr2. Cool. Alright, so 2 rules for writing the formulas. If they have equal and opposite charges, do crossover. If they have equal and opposite charges, they combine 1 to 1. If they don't have equal and opposite charges, then you do crossover. Alright, this is going okay. Alright, fill the name and empirical formula of each ionic compound that could be formed from the ions in the table. So we got a bunch of cations, and what I'm looking for here is what are going to be variable charged and what are going to be fixed charged. Now the sodium is in group 1A, so it's fixed charged. And then manganese and tin, there we go, they're not in groups that are fixed charged, right? So it's a group 1A, group 2A, group 3A, and silver, cadmium, and zinc are your fixed charged ones. So yeah, tin I'm going to have to specify the charge with Roman numerals. Manganese I'm going to have to specify the charge with Roman numerals. Sodium is good though. So my name of my cations is going to be like this: tin 2, manganese 3, and then it's just going to be sodium. Now, when I look at my anions, they're all polyatomics, right? So I'm going to have to go over to a table of polyatomics and look up their names. So BrO4 minus is per bromate. SO42 minus is sulfate. There it is there, sulfate. And then finally, CO3 2 minus is carbonate. There it is there, carbonate. Okay, so again, I always do the names first, and for ionic compounds, it's just simply the name of the cation followed by the name of the anion with no Greek prefixes. So let's go through now and figure out the formulas. Remember what we said: if they have equal and opposite charges, they're going to combine 1 to 1. And if they don't have equal and opposite charges, we're going to use crossover. So when I look at these, I see immediately that I need to do crossover in every case. So SN2 plus, BrO4 minus, 2 probromates, and 1 tin. So it's going to be SNBrO4, and then I need 2 of those. Now, sorry, didn't do that very well. I need to put it in parentheses, and I need 2 of those. So what we see is when we have multiple of the polyatomic ion, it goes in parentheses with the multiplier outside. Okay, manganese 3 plus, SO4 2 minus. This is going to get weird. 3 sulfates, 2 manganese. So it's going to be Mn2 SO4 3. Okay. And then finally the third one, sodium and carbonate. Now this illustrates an interesting point. 2 sodiums, 1 carbonate. When you have only one of a polyatomic ion, you don't put it in parentheses. Only put it in parentheses when you've got more than one of the ion. Now, I'm just going to double check all of these that I can't divide through by a common multiple, and I can't, right? So that's cool. We're good to go. All right, not too bad. Let's have a look at this guy. Naming ionic compounds with common oxoanions. So I kind of immediately grabbed a table of polyatomic anions. This is my favorite one. And then I want my periodic table because I want to check whether I've got a variable charged cation or not. So in every case here, the cation is the same. It's potassium, and potassium's in group 1. So it doesn't need to have its charge indicated using Roman numerals. So I'm just going to write out potassium 4 times. There we go, potassium. Now, I like this periodic table I got it from the book. And the reason I like it is that it has all of the molar masses expressed, except for, I think, a couple to 2 decimal places. It has the names of all of the elements with the correct IUPAC naming. So they spell cesium with an E rather than, with the AE. So it kind of just works well, like the information feels reliable, so I like that. What I don't like about the periodic table that's in the book is it doesn't have the North American conventional numbering of the groups on there, like those with the Roman numerals and the A's and the B's. Anyway, just kind of geeking out over the nice periodic table from the book. So the anion in this case is, this is the sequence of oxyanions formed by chlorine. So if you don't know, these go perchlorate is ClO4, chlorate is ClO3 minus, and then it goes chlorite, ClO2 minus, and then hypochlorite is ClO minus. But you don't have to memorize that just yet. You guys get lucky because you can look them up in a table. So here they are. It goes 1, 2, 3, 4 oxyanions, hypochlorite all the way through to perchlorate. All right, so the name of that first anion there is chlorate. Actually, I don't know why I'm memorizing them. Chlorate. There we go. Always look it up if you can. The name of the second one there is chlorite. Chlorite. The 8s always have more oxygens than the ites. The name of the third one is perchlorate. And then finally, the last one is hypochlorite. There it is there, hypochlorite. All right, so that's the names. Like I said, I always do the names first. And then now, the formulas are going to be super easy. Remember, for ionic compounds, if they have equal and opposite charges, they just combine 1 to 1. And in this case, that's exactly the case. So all of these guys just combine 1 to 1. Now, when you write the formula for an ionic compound, never include the charges, right? You never write the charges for in the formula of an ionic compound. You can write the charges in the formula of a polyatomic ion, but never in the formula of the whole compound, because the whole compound is electrically neutral. All right, let's have a look at this guy. Name each of the acids listed in the table below. Okay, so in your book, you'll learn that there are 2 types of acids. There are binary acids and there are oxyacids, sometimes called oxo acids. And so you just got to decide what type of acid you've got. It's pretty easy. Does it have oxygen present? And then what you do is just follow the rules for naming that particular class of acid, and I've copied and pasted those rules here. So one of these guys is a binary acid. It's that one there. So we're going to start with the prefix hydro, and then the other non-metallic element name is modified by adding the suffix -ic. So you're going to take the stem name of iodine, which is IOD, and add -ic to it. And then finally, you're going to finish off with the word acid. And I guess we shouldn't have an uppercase in the middle. So it's going to be hydroiodic acid. All right. So that's that. I also should point out that the first part of the name is all one word before we put acid there. All right, so we got that guy done. Check on the last one there. And then the remaining three are oxyacids, right? So what do? It says start with the root name of the anion. So we need to know the anions. So the anions are pretty easy to figure out what they are. You just take away the hydrogens and they become the negative charge. So I got 2 hydrogens there, so this must be 2 minus. Take away the hydrogens. How many did I take away? 1, so it must be 1 minus. Take away the hydrogens. The number of hydrogens taken away is equal to the charge. So that's 1 minus. So now I've got to find the names of these guys. That is sulfate. This one is hypochlorite. And then this one is perbromate. And then in the next step, what I've got to do is look at the ending, whether it's an 8 or an ite. So it says if it's an 8, it becomes an ick, and if it's an ite, it becomes an us. So start with the root name of the anion. So the first one is going to be SULF. The second one will be hypochlor. And then the third one will be perbrom. So we're just taking the ite or the 8 off the end. Right, and then I should just put in that our fourth acid was hydroiodic acid. We already finished that one. Right, then it says that the 8s become X. So we've got 2 8s, we've got sulfate and perbromate. So this becomes sulfuric perbromic. Okay, and then the ites become uses, so this becomes hypochlorous. And then finally you add the word acid. So you just got to kind of work through the roots there. I guess the interesting thing here is that sulfate, the root ended up being sulfur, and it became sulfuric acid, whereas you might think that it was sulfic acid, right, from the root there. So, and we've got to be kind of like, there's some weirdness there, and if you accidentally kind of get the stem name wrong, I'm not going to be too harsh on you, but Alex, of course, will grade you incorrect. All right. So again, we're in the same position here, but what we're going to do is we have to go backwards. We have to take the name and we have to turn it into the formula. So what I'm going to look for first is, are there any binary acids? And remember, the binary acids are going to be the hydroic acids, right? They all have a name that's like hydroic acid. And then the oxyacids, they're all either ic acids or they are us acids. So when I look at this, do I see anything beginning with hydro? And I do. It says hydro sulfuric acid. So I immediately know that this is a binary acid, and a binary acid is composed of hydrogen and one other element. So it's going to be hydrogen with a certain number of them, and then, well, it's got to be sulfur, isn't it? All right. So what I need to do now is think, what is the charge on the sulfide anion? And sulfur is over in group 6A. Sits underneath oxygen, which means it is -2. So the sulfur in here is actually present, or should be considered as being the sulfide anion, S2-, and so that means I'm going to need 2 hydrogens to get that to balance out. So this guy here, hydrosulfuric acid, is going to have the formula H2S. So we got one of them, H2S, right? There we go. H2S. So the other ones are oxy acids, right? And so what oxy acid are they? Well, we have to look to see whether the ending is an ic or an us. And if you remember, the ic acids, they're derived from 8 anions, and the us acids are derived from the ite anions. So sulfuric acid must come from sulfate. And then chlorous acid is an us acid, so it must come from chlorite. And then we've only got one left. Perbromic acid must come from perbromate. So I will have to have a look in my table of polyatomic anions to figure out what these things correspond to. So perbromate is that anion BrO4 minus. BrO4 minus. So when it makes an acid with hydrogen ions, they're going to combine 1 to 1 because they have equal and opposite charges. You need 1 H plus for every negative charge. So perbromate is, or perbromic acid is this guy. Sulfate, I'm going to look that up in my table of polyatomic ions, and I'm going to find that it is SO42 minus. So when that guy combines with H plus, I'm going to need 2 hydrogens for every 1 sulfate. So the formula will be H2SO4. And then finally chlorite. Chlorite, when I look that guy up, it is ClO2 minus. And so how many hydrogens do I need? Well, I'm going to need 1. Oh, actually, let's just not do that. They are equally and oppositely charged, so they combine 1 to 1. There we go. Right, wouldn't have made any difference if we did do crossover, but we should just remember not to. Okay, so that's it. So we've got one of them was a binary acid. That was the hydrosulfuric acid. And we knew that because it started with hydro. And then the other ones were oxy acids. And then we had to figure out whether they were derived from ates or ites by looking at the ending there, whether it was us or ic. All right. So that's how we're doing it, right? So yeah, you just got to kind of follow the rules, nice and calm. You can do it. Just don't freak out. Give yourself enough time to do it. Okay, now we got a couple of math bits. We're going to do some mole stuff and see how that works out. So it says a copper atom has a mass of that many grams, and it's not surprising, it's pretty small. And then it says a penny has a mass of that. So what we know is that 1 atom of copper weighs 1.06 by 10 to the minus 22 grams. And we also know that 1 coin weighs 2.5 grams. Okay. Use this information to answer the questions below. Be sure your answers have the correct number of sig figs. So it's going to be either 2 or 3, isn't it, right? And then it says, what is the mass of 1 mole of copper atoms? Okay. So how many copper atoms are there in a mole? There are 6.022 by 10 to the 23 copper atoms in 1 mole. That's just Avogadro's number, isn't it? Yeah. Okay. And then what I know is that a mole of copper weighs 1.06 by 10. Oh, 1 copper atom weighs 1.06 by 10 to the minus 22 grams for 1 copper atom. There we go. So that cancels out, and then that's going to give me grams per mole. Got my calculator, give that a go. So just Avogadro's number, 6.022 by 10 to the 23 times the mass of 1 copper and I know what it should be because I could look the value up in the periodic table, but don't trust that. So it ends up being 63.8 grams per mole, which is actually slightly different from the value in the periodic table. I think the value in the periodic table is 63.55, but close. Okay, so the next part is how many moles of copper atoms have a mass equal to the mass of a penny. Okay, how many moles equal to the mass of a penny? So we got 2.5 grams of copper in 1 coin, and we just solved that 1 mole of copper weighs 63.8 grams. So that would work. Grams of copper cancels out, and that would give me moles of copper in 1 coin. Well, that's easy. So I just take 2.5 and divide it by my last answer. Now 2.5 is less than 63.8, so obviously I'm going to get a lot less than 1 mole, and it ends up being 0.039 moles. That's cool, right? That works. Yep. So it's just really dimensional analysis, isn't it? Okay, next one. An analytical chemist has determined by measurements that there are 9.41 moles of carbon in a sample of acetic acid, and here's the formula for acetic acid. How many moles of hydrogen are there in the sample? So what we want to recognize is that this is about a mole ratio, right? We want to go from moles of carbon to moles of hydrogen. And how we're going to figure out our mole ratio is by looking at the formula. And what you can see here is that I get 4 moles of hydrogen, 1 plus 3, for every 2 moles of carbon, 1, 2. So there we go. That's going to be my answer. So I basically just got to multiply my number that was given by 4 on 2. 9.41 times 4 on 2. Or you could just multiply it by 2, couldn't you? So that ends up being 18.8 moles of hydrogen. There you go. Now the abbreviation for mole is MOL if you're interested. That's the official abbreviation. Okay, not too bad. Pretty easy going. All right, so now we're going to bring up the practice quiz, and the important thing to recognize is that it's just going to be a random selection of the problems that you saw in the objectives. So keep that in mind. You know, that's why we do so much work on the objectives, right? So in this case, what have we got going on here? Fill in the name and empirical formula. So I always begin with the name. So copper is a variable charged cation, so I'm going to have to put its charge in Roman numerals. So that's just going to be copper 1. And then the anion there is a polyatomic anion, so I look up its name in the table, and there it is there. It is sulfate, so the name of the first guy is copper 1 sulfate. Tin is over in group 4A, so it is also a variable charged cation, so I'm going to write tin 4. And then Cn minus is a polyatomic anion. It's called cyanide. Let's see if we can find it. There it is there, cyanide. So tin 4 cyanide. Okay, cobalt is in the same row of the periodic table as copper, first row of the transition elements. It's also a variable charged cation, so we're going to have to put the charge in Roman numerals. Cobalt 3, and then the anion there is a polyatomic ion. It's the hydroxide anion. There it is, hydroxide. So hydroxide. So there are my names. To name an ionic compound, you just give the name of the cation and follow it up with the name of the anion. So now we're going to work on the formula. As I said, I always do the names first. I don't know why. Well, I do know why. It just stops me getting tempted to include parentheses. So, prefixes. So none of these guys have equal and opposite charges. So I'm going to be doing crossover for all three of them. And then I'm going to be paying attention to see whether I need to reduce my mole ratio by a common factor. So copper is +1. Sulfate is 2-, so I need 2 coppers and 1 sulfate. So it's going to be Cu2SO4. You can see there when I have one of the polyatomic ion, I don't put it in parentheses. Okay, so now we're Sn2+ with Cn-, and I'm going to need 2 cyanides and just the 1 tin. So Sn parentheses and then my 2 cyanides. Okay. My last one, cobalt 3+. Cobalt 3+, hydroxide single minus, so I need 3 hydroxides and 1 cobalt, COOH3. Alright, not too bad. We can do it. We can do it. Okay, next one. What's got going on here? Fill in the name and empirical formula of each ionic compound that could be formed. There's 4 of them. Oh, this is that one that we saw before, right? So 2 things immediately leap out. The cation is potassium, which is in group 1A, and so it's +1. It's also a fixed charged cation, so it doesn't need Roman numerals. So in all 4 cases, it's just going to be potassium. And then for my anion, you can see that they're all polyatomics, and I just got to find them in there, but they're all of these like chlorine containing ones, right? So I just got to pick the correct name from the table. So ClO3- is chlorate, and then ClO2- is chlorite, and then ClO- is hypochlorite, and then last but not least ClO4- is perchlorate. Okay, so we got that done, and now we just need to do the formulas. So the nice thing about this is that everything is 1-to-1 as far as the charges are concerned, because they're equal and opposite charges. So I'm not going to have to worry about doing any fancy, crossover stuff. So that's cool. So they're just going to all be 1-to-1. I just got to make sure I don't make any errors entering anything, all right? I'm just checking closely that I don't add a number or miss out a number where it was needed. So because they have equal and opposite charges in every case, they all combine 1-to-1. Nice and easy problem, that one. All right. Oh, this looks interesting. This is the chemical formula for talc, the main ingredient in talcum powder, and it looks pretty gnarly. And then it says an analytical chemist has determined by measurements that there are 5.597 moles of magnesium in the sample of talc. How many moles of hydrogen are there? So this is a classic like mole ratio problem. So we just want to be a little bit careful because there are a lot of parentheses here. But what I can see is that there are, in one formula, there are 2 moles of hydrogen. And in one formula, there are 3 moles of magnesium. So if I multiply that by my 5.597 moles of magnesium, I'm going to get what I want. So I just got to do that. 5.597 times 2 on 3. And to 4 sig figs, 3.731 mole of hydrogen. You don't have to put the units there because they were given for you, weren't they? All right. Okay, number 4. More ionic compounds. Are you kidding me? All right, fill in the name and empirical formula of each ionic compound formed from the ions in the table below. So the nice thing I've noticed here is that the anions are all monatomic, so I don't have to grab my table of polyatomic ions. The other nice thing that I notice is that all of the charges on the cations in every case are equal and opposite to the charge on the anion. So I know in my formulas that these guys are just going to combine 1 to 1. So now I'm just going to check my cations to see if they are like variable charged or not. And so manganese is in the B elements, and it's not silver, cadmium, or zinc, so it's going to need Roman numerals. Same with iron, and same with copper. So the only thing that's kind of messing up here is that all of my cations will need Roman numerals, but that's hardly kind of an inconvenience, all right? So writing the name first, always write the name first. This is going to be manganese 3. This is going to be iron 3. This is going to be copper 2. And then finally, it's going to be iron 2. Now, when it comes time to write the anion, these are all monatomic anions. So what we do is we write the stem name, and then we just put the ending IDE on the end. And if you need to, you can find a list of stem names for the non-metal elements. But it's just going to be like this. It's going to be nitride, phosphide, oxide, and sulfide. There we go. All right, easy. And then the formulas, remember what I said about the formulas, because they're all equal and opposite charges, they're just going to be 1 to 1. So it's just going to be MnN, FeP, CuO, FeS. So just one of each, nice and easy. So not really much going on there. Write the name first, then the formula. Remember, for ionic compounds, we never include prefixes. That way, if you do write the name first, you're not going to be tempted to put monos and dis and tris where they're not needed. All right, this looks like a moles type problem. So an oxygen atom has a mass of 2.66 by 10 to the minus 23 grams. So 2.66 by 10 to the minus 23 grams of oxygen for every 1 atom of oxygen. And a glass of water has a mass of 0.050 kilograms. Okay, so let's see. And then it says how many moles of oxygen atoms have a mass equal to the mass of a glass of water. Okay, so the first thing I want to do is, I've got 2 mass units going on here. So I want my glass of water mass to be expressed in grams. So 0.050 by 10 to the 3 grams in 1 glass of water. Okay, and then I know that I get 1 atom of oxygen for every 2.66 times 10 to the minus 23 grams. Now, the problem is if I did this math, it would just give me the atoms, you can see here, of oxygen that are in one glass, right? That's what that would give me, and it would be a very large number, but we don't want that. We want the moles of oxygen in one glass. So I need atoms of oxygen on the bottom, and I need moles on the top, and I know that in 1 mole of oxygen there are 6.02 by 10 to the 23 atoms. So that's going to do it, isn't it? Right, there we go. And then we're going to be left with mole of oxygen for every 1 glass. Okay, so not too bad. 0.05 by 0.05 by 10 to the 3 times 1 on 2.66 by 10 to the minus 23 times 1 on 6.022 by 10 to the 23. So it turns out that there is 3.12 moles of oxygen in a glass. Now what I know from the periodic table is that 1 mole of oxygen is 16 grams, right? So if I do 16 times 3.12, it should give me my 50 grams, right? So times 16, and sure enough, it came back 49.9. So, considering a mole of oxygen only weighs 16 grams, I know I'm going to need several moles of oxygen to get up to 50 grams. All right, let's have a look at this one. This is one where you have to decide if a pair of elements forms an ionic compound or not. And if they do form the ionic compound, you're going to have to write the name and the formula for it. So the first thing to check is, do they form ionic compounds? Remember, an ionic compound forms between a metal and a non-metal. So what do we got here? We got cesium and we got iodine, yellow and green. That's a metal with a non-metal, so yes, it forms an ionic compound. Then we've got sulfur with fluorine. They're both non-metals. So no, hallelujah, that's one less that we have to figure out the formula for. And then we've got lithium with oxygen. Yes, that's a metal with a non-metal. So it forms an ionic compound. And then finally, we got calcium, which is a metal, with bromine, which is a non-metal. So yes, it forms an ionic compound. Okay, now we go and name the ionic compound, and it's always the name of the cation followed by the name of the anion. Now, what we want to check is does our cation need Roman numerals? And our rule that we have was if it's in group 1A, 2A, 3A, or is silver, cadmium, or zinc, it doesn't need Roman numerals. So cesium is in group 1A, lithium is in group 1A, calcium's in group 2A, so none of our cations need Roman numerals. So they're all just going to be cesium, lithium, calcium for the name. Now, when we come to name a monatomic anion, like we have here, just formed by a single element, remember it's the stem name and the ending IDE. So this is just going to be iodide, and then it's going to be oxide, and then finally bromide. So there we go. All right, so that's our 3 names. Remember, we get a free ride on the second one. And then finally, we just have to figure out the formula. And remember 2 rules for figuring out the formulas. That is, if they have equal and opposite charges, they combine 1 to 1. And if they have different charges, you use the crossover. So for naming out, for the charges on our non-metals, they go -1, -2, -3. So it's all about what group they're in. So cesium's in group 1A, so it's +1. Iodine is in group 7A, so it is -1. So those guys have equal and opposite charges, so they combine 1 to 1. Lithium is also in group 1A, right at the very top, so it is +1. Oxygen is in group 6A, so it is 2-, so we have to do crossover, and we need 2 lithiums for every 1 oxygen. Finally, we've got calcium. Calcium is in group 2A, so it's going to be +2, and then bromine is in group 7A, so it's going to be -1. So what that means is we need 2 bromines for every 1 calcium, so it's going to be CaBr2. These guys are getting really skilled at doing this. Alright, here's this last question in this practice test, and you guessed it, you're given the name of an ionic compound and you have to give the empirical formula. Now I know it's an ionic compound because in each case it is a metal, lithium with iodine with a non-metal, magnesium with bromine. So metal with non-metal immediately tells me I've got to use the rules for ionic compounds. So how am I going to figure out my formula? Well, I need to know my charges on my ions. So lithium is in group 1A, so it is +1. Iodine is in group 7A, so it is -1. They have equal and opposite charge, so they combine 1 to 1. Magnesium's in group 2A, so it is 2+. Bromine is in group 7A, so it is -1. So I've got to do crossover because they have different charges, so it is MgBr2. Alright guys, so that was a little bit of a talk about the lab, then we worked through some of the objectives, and then finally we worked through a practice quiz. Remember, there's a more detailed video about the labs that I posted a link out for, so check that out if you've got more questions. Okay, that's enough from me for now. Hope you found the video helpful. Catch you around.